All right, so let's start what we left before. So we talked about the enthalpy change. Of the reaction. So we actually talked about the simple rule. So enthalpy change of the reaction should be equal to sum of your products, enthalpy change of formation, minus the sum of the reactions. So this is something you can do. I'll show you some example here. We can try to do the propane. Okay, so it's the propane combustion reaction. So the first thing which you need to do is, once again, we need to do stoichiometry. We're going to balance the equation here. So what I'm going to do is I'm going to try to put 1 over here. So I can put at least 3 for carbon dioxide, because each propane has 3 carbons. And also each propane has 8 hydrogens, so I'm going to put 4, because each water has 2 hydrogen over there. Okay? So once we balance the numbers for the carbon and hydrogen, which will give us like 6 oxygen here, 4 oxygen here, right? Then 1 oxygen, but 4, 3, but there are 2, so it'll be 6, 4. So in total, we have 10 oxygen. Okay. So to make the 10 oxygen on the left side, we're gonna do 5 diatomic oxygen molecule. So if we're done with the balance in the equations, we're just gonna do this one. Okay. So to do that, you need to have sum of the product, so enthalpy change of the formation of carbon dioxide is about 393.5 kilojoule per mole. And then this is the water is about 295.8 kilojoule per mole. Okay, the oxygen is usually just nothing, 0 there. And the propane is about the 3.8 with me. 8, yeah. Okay. So what I'm gonna do is we're gonna sum up this one minus sum of this. Okay. So to do that, I'm gonna do. But here's the thing: we have a 3 as a coefficient for carbon dioxide, 4 as water. So we're going to multiply that enthalpy change of the formation of each by its coefficient number. So it'll be 3 times this number. Okay. And we're going to add this number to this one because they're both products. So this will be not 4, right? 4 times 295.8. Then, now we sum up all the products with the coefficient number. We're gonna do minus with this one. So we don't have to worry about the oxygen because it's 0. But we have a 1 propane, so the 1 times negative 3.8. So this will give you some number that is your enthalpy change of the reaction. Should be about 2,219 kilojoule per mole. Yeah, you can do this. Yeah, you can try to plug those numbers in your calculator. 3 times negative 393.5, 4 times 295.8, and add them all, and minus that your enthalpy change of formation of your the reactants there. Okay. Yeah.
Is this supposed to be negative 393.5?
Oh yes, yes.
Or positive 3?
Perfect.
Both of them are negative?
That's both negative. Yes. Perfect. Oh, that was a good catch. Thank you. That's very good. Yeah. that's the. So if you do all that numbers plug into the that equation we're gonna follow, it should be about like a negative 2,000. Do you get the number?
Oh, I haven't.
Oh, okay. I mean, you can try it.
Yes.
Okay. Okay. All right. So if that is the case, let me see. Let me try. Let's try this one. Okay. How about the? Okay. Can you guys try this one real quick? Okay. And then entropy change information is 5.6. This is a bit tricky, but you can. I'll give it about 3 minutes. It'll take some time. So it's now we're using butane instead of propane. It should be the same procedure, same calculation work, but just different numbers. Okay, about 1 or 2 minutes. Okay, about 1 minute. We'll do this too. It takes some time, okay, but make sure you guys put all the numbers in, and eventually get the answer. Okay. All right. So here's what I'm gonna do. This is a bit tricky, so you can listen to me kind of carefully. So I'll try one over here. Okay. Oh no. Okay. Sorry, it's actually my mistake. Could you guys actually do this again with that? I'll show you. Okay. So it was actually 2n plus will be 10. So I'm gonna put 1 over here. So I'll just show you. The 4, so I'm gonna put 4 over here. But it's 10, so I'm gonna put 5. Okay. But the problem is if you do this in this way, it'll be 4 times 2 is 8, and 5. So in total you have a 13. But this has to be in diatomic molecule, so you can do this one. But you can also do this one. So you just try to double all the coefficient number, 8 and 10. So now you have some other, well-balanced equation here with the integers here. So basically what I'm gonna do is the same. 8 times 392.5 plus negative. And then we have now 10 times negative 2, 85.8. Okay. And then minus, there'll be 2 now, so it's 2 times negative 125.6. So if you do this one, there should be about negative 5,000, was it 754? Okay, 50. Yeah. Okay. Point. Perfect. So here's the enthalpy change of the reaction state. But this is kind of a tricky because if you look at this one over here, this amount of energy is coming from what? 2 butane. 2. Okay. So for butane combustion, enthalpy change will be half of this one. Okay. So that will be butane enthalpy combustion will be -2, 7, no, 7 per mole for butane. Okay. For oxygen or for carbon dioxide for water, you should be divided by that coefficient number. But we're mainly doing what? Organic compound combustion, so it will be actually -2,876. So it's a bit tricky because you have to double. So you have to have a double amount of the compounds making double amount of heat. If you actually want to make it from the 1 mole to be 1 mole, it has to be half. Or is it what? So per mole has to be about it. It's kind of tricky one. I don't think I'm gonna put this in the exam, but just let you. Okay. So let's do one more, and we'll move on. Okay. How about we do? Pentane. All right, just last one. We will definitely move on. Okay, over 2 or 3 minutes again. Oh, this one is. Okay.
First one, 0.8 or?
Oh, it's a 0.8, yes.
Okay.
Yes. Yes, -4, -146.8. Okay. About 1 minute, we'll do this together. Move on. Okay, about 30 seconds. Okay, so I'm just gonna do the same thing here. It'll be 1, so I'm gonna put at least 5 carbon dioxide because there's 5 carbons in it. So it'll be 12, so I wanna put at least 6 over here. So that makes the 10 oxygen here, and this is 6. So then we'll in total you have 16, so it'll be 8. Okay. So then what I'm gonna do is pretty much the same what we did. So 5 times -393.5 plus 6 times -285.8 and sum minus. So we don't care about this one, it's just 0. It'll be 1 times -146.8. So it should be -30,535. Perfect. Yes. In this case, we kept this one in the 1 mole, so it's just good at that point. So that is our enthalpy change which is what? Your propane combustion, which is negative. Totally makes sense because it has to be what? The exothermic reaction. Okay? So I think I can move on, right? So this is a pretty good review that we did on last Friday. So there's another way we can measure the change in enthalpy of the chemical reaction. We use a Bohm enthalpy. So Bohm enthalpy is simply same as Bohm energy. And this actually indicates the amount of the required energy to break the bond, a specific bond, bonds about like a 1 moles of it. So if you have a 1 moles of like bonding, like you have this type of bonding here, so you want to break it, right? So then obviously you need to do the work to the system, right? So that means your Bohm enthalpy, well, you can say Bohm energy, will be always positive. Because that means you want to break something, you have to do something to the compounds that will actually like is positive, the gaining energy. So if you have a 1 mole of this diatomic molecule like chlorine, you can break it. There's only 1 bond in each compound, right? So it'll be 1 moles of bond. To break it, it may cause like 242 kilojoule amount of energy. Then Bohm enthalpy of this bond will be 242 kilojoule. And obviously it's per mole because it's 1 mole. Make sense, right? Okay. Oh, and also in the gaseous phase. Okay. So we use gaseous phase because it's easier to estimate, quantify the numbers of bonds that broke. As you know, if you do it on the solid, the liquid phase, the one in inside, it's not hard to make the chemical reaction almost at the same time. It's always easier to measure in gas phase. Okay. Make sense, right? So this is something we're gonna use for get the enthalpy change of the reaction with this number. So the what I'm gonna do is it should be equal to the sum of the bonds that are broken, okay, and minus the sum of the bonds that are formed, newly formed. Okay? So obviously this will happen in where? This will happen in reactants, right? Because the reactants will break their bonds to be new compounds. So the new bonds will be made in their products. So this is kind of a vice versa to what we just did. Because we used the enthalpy change of the formation to just sum of the products minus reactants, right? But for Bohm enthalpy, we're gonna do the bonds broken minus bond formed, which is actually coming from the reactants minus the products. Okay, so if you have a very simple combustion reaction like this one, obviously you can balance this one like this, right? And then for this one, this is kind of challenging because you have to know the chemical structure of each reactants in the compound. So I will show you the structure of the methane here, which looks like this. Okay, and there'll be 2 diatomic oxygen molecule, gas molecule, looks like this. It's a double bond here, and then carbon dioxide has also double bond on each side with oxygen. So this is carbon dioxide. And water, it just looks like this, with a bit of bent portion, bent shape. So this looks like this. Okay. Then it's actually quite easy from there when you find out the structure, because to make the carbon dioxide from the methane, to make the water from the oxygen here, you have to break those 4 CH bonds. So you have to break, there's a 4, right? 1, 2, 3, 4 times CH bond enthalpy. Okay. Okay, so this is the 1, and you're gonna break 2. You're gonna break 2 O double bond. So those are the sum of your bonds enthalpy that are going to be broken. Okay, and minus. So if you look at the product side, now you'll see the new bonds are formed after chemical reactions. There will be 2 carbon and oxygen double bond. There are 2, right? 1 and 2. So times 2 bonds. And plus, there's a O oxygen hydrogen single bond there, but it will be 1, 2, 3, and 4. So actually it will be 4 times O hydrogen, oxygen hydrogen bonds. Okay. So then the only thing you have to do is also this number will be given, but you just need to plug the numbers. Okay. Then OO was about 395, 490. Oh, yeah. And this is a 799. This is about 465, 63. So obviously, once again, those type of question, you'll see the table of the enthalpy change of the formation. For this one, you're gonna get the table of enthalpy, bond enthalpy, bond energy number. So you just need to plug those numbers in, okay? And then the answer I think should be negative 820. So for methane wise, it will be per mole, but anyway. So this is, I think, this is another way you can get the enthalpy change of the reactions by using bond enthalpy. So previously we used the enthalpy change of the formations, but this is another way you can do the similar job there. The number will be won't be identical, but very similar to each other. You don't have to know why it's not identical, just similar, but this is another way. So what I'm planning to do for the exam is this is, I think, too much, because you have to know all the different types of compound structure to get this question, right? So this exactly the same question will be on the exam. So if you just know how to do this, you'll be just fine. Okay? So that's why I'm showing you all the structure I just today. So just this one, exactly the same problem will be on the exam and nothing else. Because I think you only get to this part when you know about the Lewis structure. I don't know if you guys taking Gen Chem 2, but you'll get the Lewis structure, meaning you're going to find out the chemical structure of the compounds by doing those the lecture maybe next semester. But for this one, that's it. Okay, makes sense, right? So just this one. All right. So we're actually quite done. We just looked over the two different ways to get the enthalpy change of the reaction here. There's another rule we can talk about in this thermochemistry is Hess's rule. Hess's rule. Okay. So Hess's rule is we're using the enthalpy change as a state function. So if some reaction is happening in the stepwise, we can put it in the one combined reaction using as a characteristic of the state function. So what I mean by that is if you have like A becomes C, this is A plus B becomes C. Okay, this is the first step. The second step, C becomes the D and E. Something like this. So this is the second step. And then overall, you can actually combine. And so there will be the enthalpy change in here and here. The sum will be the same as combining these two reactions. Because it's a state function means it will be determined by only the final and initial states. Final and initial state. So the gap between the final and initial state, it will determine the state function. So we'll never change how it get to there. So here's the thing. If you have a mountain over here, so you went over the mountain, and now it's here. So maybe this is a 0 meter sea level. This is 100 meter. This is a 200 meter. Okay. So the state function is just these two. Your final position, initial position. So in the stepwise, it doesn't matter. If it matters to the path, how you move to that final position, we call them path function. Because it's depends on the path, how they move. But luckily, our enthalpy change is actually the same as the heat energy at constant pressure. Is a state function. So if you can just combine these two, will be the same as A plus B plus C, C, D, E, and combine these two enthalpy change together. So if it's 100, this is 100. This will be automatically 200. That works. Okay. And then there's another one I want you to remember is in this way, if you see the same compounds on the left and right, you can cancel. So meaning this is what we call intermediate, reaction intermediate, that can be canceled. It can be abbreviated in your final equation. So you can just put, so if A plus B makes C, and C eventually in the second step become D and E, you can just add them all together, which you can add those numbers for each enthalpy change, and the final enthalpy change will be the same. So you can remove this one, and the A plus B becomes D and E. With this enthalpy change, that works. Kind of makes sense. Okay. So I'll give you one more example here, and then I'll show you the practical problems. Because there are several things I want you to know. So A plus B becomes C, and C becomes D and E. Okay. Here. So like I said, if this is maybe plus 100, this is maybe negative 50, you can just write down, cancel the both sides here when you combine. A plus B becomes D and E, and you just add them all, so B plus, okay? So A plus B become D and E will become plus 50. For enthalpy change, we just know by combining these two and also the enthalpy change over there. Okay, so this is first rule. This is the first rule of the Hess's law. Okay, and the second rule is this one. Whenever you have so for example, you say A plus B makes 2C. Okay, 2C. Okay, and then 1C becomes D and E. Okay, so what I'm gonna do is I want to combine this one. Okay, I want to combine this one together, but the thing is they don't add up with the intermediate y's. Okay, so in this way, to make it simplify, what you can do is you double this one. So be double on the left and right. So be 2, 2, 2. Okay, and then make sure you also double that enthalpy change. Okay, because it's a double. So more molecule will make more enthalpy change. So then now, when you combine, you can cancel them. Okay, so in final equation, you're gonna get A plus B become 2D and 2E. And what you can do is what? Plus 100 plus negative 1,000. So it will be negative 900 over there. So this is the second rule. If you want to multiply the both sides to get the more simplified final equations, make sure you also multiply that enthalpy change by the same number. Okay? That's the second one. Okay, move on, right? Okay, so this is the last one. Okay, so the last one is here. Let's say we have this will become maybe 2. Just see over here, and then what we're just gonna do is the D plus E becomes C. Okay, so in this case, we cannot do anything. It doesn't make any sense because the C, those both are as C is their product. So in this case, maybe this is 100, negative 200 over here. What you can do is you can flip the equation. That's okay. So if this is A plus B makes C, and this is D plus E makes C, right? But maybe you can change. You can flip this one to C makes C. So you make a reverse reactions, and then only thing you have to do is change the sign. So this will be once negative 200, but when you flip it, it's the positive 200. So it's the other way. It was maybe it was 100. When you flip it, it will be negative 100, because it's actually going the other way. So the change will be actually the other way. So the sign will be changed, and then you can add them all, A, B, and it can be canceled now, right? And then E, because on the opposite side now. And then the only thing you have to do is once it was negative, multiplied by negative 1, so it'll be plus. So if you add them all, this final equation will have a 300 as its enthalpy change. Make sense, right? Perfect. So let's make it a bit more tricky. Okay? Maybe you can try this one. You can try A plus B makes C over here, okay? And D plus E makes maybe 2C, okay? And this is maybe plus 100, negative 300, okay? Maybe can you guys try this one? Can you guys combine and get the final enthalpy change? Okay, this will take some time, so I'll probably give you like 2 or 3 minutes. Okay, about 30 seconds. Okay, so here's the thing. What you can do is you can try to get the final equation to make it, maybe you can try to do double this one, so you can double, and you can flip this one, okay, so it'll be positive. Okay, so when you can do the 2A, if you want to keep A plus B form, this will show you 200 plus 300 is 500 as the enthalpy change for this reaction. It could be different if you try to eliminate by actually making half of this one and flip it. That's okay too. But the thing is, you know how to use the 3 rules in Hess's law. You can make the enthalpy change for any specific final equations. Okay. All right, so let's try to do practical one. Okay. So if we have carbon interact with the oxygen, it makes the carbon dioxide. Okay. And then you also have a carbon monoxide interact with the oxygen that makes carbon monoxide. In this case, I want to make the final equation looks like this. Check. No, sorry. That was this one. Okay. Yeah. Can you cut? Oh, yeah. Maybe you can try this one real quick. Okay, about 2 minutes. We'll do this together. Yeah, I mean, you can try to. Okay, about 1 minute. We'll do this together. Okay, don't worry about it. Just, okay, about 1 minute. Well, I want to make this final equation here, and just show us what might be the interpretation for this one using these two. About 30 seconds, we'll do this together. Okay, yeah, this is a bit tricky. All right, so let's do this together. So here's the thing. The first thing what you need to do for this type of question, you need to look at the final equation first and how they place the products or the reactants here. So for this one, your product is what? Carbon monoxide. The carbon monoxide is in your this equation here. But the problem is this is on the left side. So that's the indication that you need to flip this one. So you're gonna flip this one, okay? So that means you need to multiply this number by -1 before you combine, okay? So this will become what? Positive, right? And then here's the thing, when you flip this one now, okay? This one over here, right? And then when you combine these two, okay, obviously you have this one cancel, right? So there's no more carbon dioxide in the final. But also another thing here is this one. If you look at this one here, it's a 1, 1, 1, right? So then it would be, this is the same as 2/2. Okay? And you have a half of the O2 is right here. So this can be gone, and this can be just 1. Okay? So now you have only, so just 3. So this is on the left side, and this is on the right side. This is your final equation. Okay? So only thing you have to do is multiply this number by -1 because we flipped it, and now you're just gonna combine these two. Okay? So it will be about -100. Makes sense, right? So, okay. So I'll just stop here today, and we'll probably